So first I would like to thank the organizers for this invitation in this very nice place, this nice workshop. Oops, it's a bit, okay. So, so today I will give some, I will show you some new results that we have obtained in the context of fractional quantum Hall effect, more specifically the realization of fractional quantum effect in bosonic systems. So maybe two initial remarks. The first one, when you give a talk about fractional quantum Hall effect, there is a high chance that you have to cite Duncan almost all the time, so at every slide. So if you don't see his name, it's just a mistake. I mean, he had so many contributions in the field and still have so many that in principle you should basically mention him all the time. The second remark is we had lectures last week about various aspects of topological phases. And I can see a few familiar faces in the audience. So I hope that today you will see other aspects, or more precisely, that we make contact between what you have learned last week and some recent developments. OK, so first I should acknowledge the people that have actually done the work here, and especially Scott Garrett from Princeton University. He's a postdoc there, and he did most of the heavy lifting of this project. So the other people are Cécile Plin at the Max Planck Institute, Chong Wang at Harvard University, Roger Bong at Pittsburgh University, and Sim Thiel at MIT. So you already had an overview of the fractional quantum Hall effect, but let me just briefly remind you what we are dealing with. Usually when you think about fractional quantum Hall effect, you're thinking about an electron gas confined in 2 dimensions under a strong magnetic field. That's the usual picture for the whole bar. Since we are dealing with these fermions or these electrons at the strong magnetic field, you have Landau levels. You can forget about the spin for the moment, and you have this completely degenerate bands with a non-trivial Chern number, which are separated by the cyclotron gap. When you have a finite size sample, remember that the number of orbitals that you have, or the number of levels that you have per Landau level, is just given by the number of flux quanta that goes through the system. So you can define your fitting factor as nu as the ratio between the number of particles and the number of flux quanta. And of course, the business here is what's going on when you have a partial fitting of, let's say, for example, the lowest Landau level, and you turn on strong interaction. This is how you drive the system into the fractional quantum Hall effect. With all the warnings, I mean, that Duncan just gave you, it's convenient to work within the lowest Landau level and using the symmetry gauge. So the one body wave function are just some z, which is the electron coordinate, x plus iy to the power m, which is just the angular momentum in that case, times the Gaussian weight that gives you this fuzzy shape. And when you write down a many-body wave function where all the particles live in the lowest Landau level, you can write it down as a polynomial in the electron coordinate. Let's say you have an electron here from z1 to zn and some Gaussian weight. And as Duncan showed you during the talk, when, for example, you do hexagonalization of, let's say, some elastic interaction, like the Coulomb interaction projected onto one Landau level, you have, for specific fitting factor, you have one lowest energy state separated by a gap from all the other excitations. So you have gap bulk, but when you look at the edge of the system, if you use like an open system, you have gapless chiral edge mode. If you restrict if you assume that the cyclotron energy is much larger than all the other energy scales, then you really have a strongly corrected system. Basically, when your effective Hamiltonian is just given by the interaction projecting onto the lowest, onto one Landau level. And as it has been discussed, it's a system where it develops into topological order, so where the excitation carry fractional charges. They can have fractional statistics, namely when you exchange two particles, you get a phase factor, which is not 0 over pi like you have for bosons and fermions, but you can get something in between. And the exchange can also be described in more generic way by matrices, and this leads to the non-abelian statistics. So you already seen this wave function this morning. This is the Laughlin state. Let's say if you do a numerical simulation on a clean sample, it's a very good approximation of the actual ground state at the filling factor 1/3. And it has fractional charges excitation, which charge 1/3 of the electron charge plus or minus and have fractional statistics. But they are abelian, so they are just described by phases, not by matrices. You can look at the edge excitation. It corresponds to a chiral U1 boson with a linear dispersion relation. And if you can construct these excitation this way, so it really looks like the usual chiral mode, where you have the energy here at the function of momentum, you have your dispersion relation, which is linear. The only trick here is that you assume that you have 2 empty orbitals for between at least 2 empty orbitals between 2 consecutive occupied ones. And you can count how many states you can create for at a given energy. So that's your ground state where you fill all your states below the Fermi level. When you look for one excitation, that's the only option. This one is forbidden because of the exclusion principle. And this is the 2 options that you have at the other energy level. So you get this specific counting for the chiral edge mode 1, 1, 2, 3, and so on, that we will use later. So one feature of when you restrict to a single Landau level is the particle hole symmetry. So right now we're dealing with spinless fermions. So it's an exact symmetry for a single Landau level, and as soon as you only consider 2-body interactions. So if you take your Hamiltonian for your 2-body interaction projected onto, let's say, the lowest Landau level, and you compute its particle hole conjugate, you get exactly the same spectrum up to some energy shift. And this particle hole symmetry will map the filling factor nu to the filling factor 1 minus nu. So basically, if you have one occupation, one configuration in the occupation basis, where you have like 4 occupied orbitals, the particle hole symmetry will map this configuration here to this one. You just switch, replace an empty orbital by an occupied one, and vice versa. And you can also see this symmetry in the experiments. So this is the usual plot of the longitudinal resistance, this part here, and the whole resistivity here, where you see the nice plateau for the whole resistivity and the 0 of the longitudinal resistance as a function of the magnetic field. And you see around 1/2, which is the point, the filling fraction, which is invariant under this transformation. It maps 1/2 to itself. And you see that you have fraction on both sides, which are related by the symmetry, like 7/3 and 6/3 and so on. And then what half? You see that there is no 0 of the longitudinal resistance. There is no gap phase. It's a gapless phase that is described by a composite Fermi liquid. So that was for fermionic systems. But there are proposals beyond to the electron gases. I think it backs to the work of Wilkin and Gunn, where they proposed to realize the fractional quantum Hall effect in rotating cold atom gases. We are also now proposal in lattices, and even if people didn't reach yet the fractional quantum Hall effect in cold atoms, they have realized recently the Haldane model, which is the analog of a Landau level just with 2 bands and a non-zero chain number for each band. You can think also about optical cavities. So you have lots of freedom to both change interaction compared to the interaction that you usually use in an 2D electron gas, but you can also replace fermions with bosons. And even if you do that, you still have fractional quantum Hall effect. So the simplest setup that you can imagine, for example, the one that was introduced for rotating gases, is basically to have bosons that interact through the S-wave scattering. And the interaction is just the contact interaction. So when you rotate your electron gas and you have the confining potential, you're in a situation which is exactly like particle have at the proper frequency. It's like having particle in a magnetic field. So the nice property of using this interaction for boson is if you project onto the lowest Landau level, the Laughlin 1/2 state is actually an exact solution of this model. So yet, this is densest zero energy state for this specific interaction projecting onto the lowest Landau level. So you already know that the physics should be there for this specific setup. But of course, you have other fractional quantum Hall states that emerge in such a model. And you might wonder, is there actually any difference between dealing with fermions or bosons from this perspective? Well, the first one is, do we have any integer quantum Hall effect? So do we have the analog of completely filling one Landau level, which is a topological insulator, this first example of topological insulator. So you realize that if you use bosons in an insulator, you have some issue here. The first one, we need some non-trivial band. So we need a system with, we can think about a lattice where the lowest band has a non-zero Chern number. You can think about the one Landau level. But it's not enough. I mean, if you have like a small dispersion relation here, all your bosons will condense into the state with the lowest energy of your band. So you turn on strong repulsion. That's something that you have for free in these cold atoms. But if you do that for such a system, at the filling factor nu equal 1, so when you have as many particles as you have orbitals in your band, in your lowest band, what you get, the signature that we have from all the numerical simulation, is we get a Moritz state. So the Moritz state is a generalization of the Laughlin state that has these non-abelian excitations. So actually, if you want to obtain an integer quantum Hall effect for bosons, you still one more ingredient. This additional ingredient is you need 2 copies of the band, which you can get just by imagine that your bosons have an internal degree of freedom, like up and or down. Call it spin, but it can be any physical degrees of twofold degrees of freedom. In that case, this is how you get a bosonic integer quantum Hall effect with the Hall conductance that is also quantized at a value 2 square over h. And in the context of symmetry protected topological phase, that's the simplest example that you can build for a bosonic system in 2 dimensions. And we have, since a couple of years, we have several numerical evidence that if you take such a setup here, you will have a bosonic integer quantum Hall effect. So yes, we have also the integer quantum Hall effect for bosons, like with fermions, but we need some additional ingredient. So what about the particle Hall symmetry? So how to get, let's roll back a little bit and focus first on the fermionic system. So if I give you a wave function, let's say the Laughlin state, and I ask you compute the particle Hall conjugate of this wave function. There are 2 ways to do that. The first one is to apply the particle Hall transformation to each state of your many-body basis. We know exactly if you have your one state in your many-body basis, just the occupation number, you know how to conjugate it by the particle Hall symmetry. So in principle, you're able to do that for the full state. But you see, it deeply relies on the notion of fermions, because you really switch from one occupied orbital to an empty one. But actually, there's another way to think about this particle Hall conjugation, and it's namely the following. Let's say you start with a field Landau level. So in this situation, I have 4 flux quanta and 4 particles. Now let's add 3 flux quanta to the system. In the usual picture of the quantum Hall effect and the fractional quantum Hall effect, adding flux quanta will create Hall or quasi-Hall excitations. So if you want here, I start from integer quantum Hall effect and create 3 Hall's excitations. And then I ask these Hall's excitation to form a Laughlin state at nu equal 1/3. And that's just another way to rephrase the particle Hall symmetry. It's just condensing your excitation of the integer quantum Hall effect into a specific fractional quantum Hall state. Now, the recipe can be changed just by changing your input state. So instead of starting from a field Landau level from the integer quantum Hall effect, you can start from a Laughlin state and start neglecting excitations and ask this excitation to form another Laughlin state. That's the Haldane Halperin hierarchy. You can do that starting from non-abelian states. You get another hierarchy. And the idea by Wang and Sentil was to say, for a bosonic system, what we have to do is to substitute the integer quantum Hall effect, the one that we have for fermions, by the integer quantum Hall effect for bosons. And that's just a way to realize a particle Hall symmetry. But we want to see if the symmetry is present in a microscopic model. For the time, it's just a recipe to create a wave function from another one. So the goal is the following. We want to show the existence of this emergent particle Hall symmetry. It's not an exact symmetry, so especially when you do finite-sized numerical simulation, you don't expect to have an exact relation between two spectra. So we take the simplest setup that we can imagine. We have bosons in the lowest Landau level. We have some integral degree of freedom for this boson, like a spin 1/2. It's just two components. It could be two, whatever, like a layer index or some orbital index. And we use the same interaction I've introduced before, the contact interaction, which is insensitive to the spin. So it means that you have an SU2 symmetry in the system. But it's not really mandatory. You can break slightly your SU2 symmetry and still have a U1 cross U1. You will have similar results. Before that, I need to introduce a generalization of the Laughlin state when you have an integral degree of freedom. It's called Halperin wave function, and this is the type of wave function that you write down. So now remember, we have particles, boson with a spin up and with a spin down. And you have some Laughlin factor for the spin up, a Laughlin factor for the spin down, and some inter-species correlation. And these integer here, the M should be even if you're dealing with bosons, just because your wave function has to be symmetric when you exchange two particles with spin up. Same story for the spin down, and there is no constraint on N. So for the time being, I will focus on the specific case where I take two here, and one here. And the reason why is the following. The interaction that we use for the model is actually, the state is actually the exact zero energy state. That's the densest zero energy state that you can have for this repulsive interaction. It corresponds to the filling factor 2/3, and it's a spin singlet. And in terms of edge mode, we have two propagating edge modes, one charge mode and one spin mode. So let me just give you the answer, or more precisely where we want to reach at the end of the day. So if you think about the particle Hall symmetry for fermions, for spinless fermions, so we basically have the integer quantum Hall effect that you can connect by the particle Hall conjugation to just an empty system. Remember, you transform all the occupied orbital into empty ones. So if you start with a perfectly filled band, you map it to the nu equal to 0, the empty system. The Laughlin 1/3 state will be mapped to its particle Hall conjugate. And at 1/2, you have a gapless phase described by composite fermion Fermi C. What do we expect for spinful bosons? So there, we have the bosonic integer quantum Hall effect for nu equal to that you map to the empty system. And we want to see if there is any emergence of a particle Hall symmetric state related to the Halperin wave function. And the other ingredient is what is going on at nu equal 1. So the transformation, the particle conjugation for bosons map actually nu to 2 minus nu. So the invariant filling factor is nu equal 1 for this case. That's for the singlet sector. You can also look at other spin sector, but I don't want to talk about that right now. When you try to, when you want to analyze the fractional quantum Hall effect, numerical techniques are really important because it's a key tool to understand what's going on. And you have several options. maybe the simplest one is just to try to propose some model state and analyze what's going on. But maybe the most unbiased way is just to say, look, we will take a small number of particles, and we write the Hamiltonian for the small number of particles and just brute force diagonalize it. It's a finite size calculation that you can realize on a closed geometry like a torus or a sphere. And that's really helpful to grasp what's going on and what kind of phase can emerge in these systems. But we also have more powerful methods these days, like the infinite density matrix normalization group. So this is tightly related to the notion of matrix product states that we discussed last week. Basically, it's an algorithm. If you think about all the physical state that you can imagine, the kind of states that we are interested in, especially in this realm of topological order, are states with a very specific entanglement structure. And the matrix product state is a very powerful way to represent this specific state. So this kind of algorithm actually tried to minimize, to find the lowest energy state that has a very specific structure from this perspective. So in the context of fractional quantum Hall, it has been introduced like a few years ago by these three young people here. And it's really a powerful method to probe topological phases. And the reason why behind that is really the entanglement. In these topological phases, the entanglement entropy will grow like, basically, if you take your system on a cylinder, it will grow like the perimeter of the cylinder, not the length. So if you compare to exact diagonalization, which grows exponentially with the system size, the complexity related to this kind of algorithm grows like the exponential of the perimeter. So you have an exponential gain to use this technique. And it's also tightly related to the notion of entanglement, as I already mentioned. So let me introduce another concept that was proposed by Lee and Haldane in 2008, which is the notion of entanglement spectrum. So let's start with a quantum state psi at t equal to 0. Imagine this is the ground state of your system. And by some Gedanken experiment, cut the system into two parts A and B. So you have like a very simple example here with 2 spin 1/2. And let's say you cut your system into two, so the left spin is going to be the part A, and the right spin is going to be the part B. You can compute the reduced density matrix by tracing out the degrees of freedom for the region B. So you take your projector onto the state psi, and you just trace over B. And you can rewrite this reduced density matrix as the exponential of minus some entanglement Hamiltonian. And the spectrum of this entanglement Hamiltonian is the entanglement spectrum, the psi I. So usually you can label these levels, the entanglement energies, by some quantum numbers. That's exactly what we do here. So let's say for psi, you take a product state with two spin-ups. Then the entanglement spectrum is here. So you have a single level at 0. And with a quantum number as ZA, which is just the projection of the spin along Z for A, which is 1/2. And when you take now a product state, so here it's a triplet state for SZ equal to 0, you get these two levels in your entanglement spectrum. So already there, you can see that the entanglement spectrum allows you to make the difference between a product state and an entangled state. But it's much more than that when you turn to topological phases. Especially if you look at these model states, be it the EQHE model for 1D system, or let's say the Laughlin state. If you compute the entanglement spectrum for such a state, you have much less entanglement levels that you expect for a random state of exactly the same number of particles, the same system size. It's exponentially less. And actually, if you look at both the number of levels and the dispersion relation, so the relation between the entanglement energies and the quantum numbers, like the momentum, they are really related to the edge excitation of the system. If you do DMRG calculation or iDMRG calculation, it's a free byproduct of the simulation. So it's very easy to have a look at the entanglement spectrum. So let me give you an example about the integer quantum Hall effect, but it's exactly the same calculation if you do the Laughlin 1/3. So remember, that's how you count how many edge modes you can have with a given total energy. So let's say now you take a droplet of your quantum Hall liquid, and it's circular, so it's easier to do the calculation, but there is nothing special about that. And we cut a small region, a small circular region, A, so a small disk, and we do this calculation of the reduced antimatrix, and we look at the spectrum, or the entanglement spectrum. This is what you observe here. These are the entanglement energies as a function of the momentum along with this virtual cut here. And you see this very nice linear dispersion relation, which is exactly what you expect for a chiral edge mode. But it's not only the dispersion relation. If you count how many levels you have per momentum, it exactly matches the prediction that you have here. So that's one of the very neat features of this topological phases and more generally about topological order. The excitations are already encoded within the ground state. Remember here, it's a calculation where you start from the ground state of the system. And still you're able to extract information about the edge excitations. But it's also a tool. You can use the entanglement spectrum to identify the phase that you have in your numerical simulation. So let me give you one example. So in the model where you have with the boson interacting with delta interaction, the internal degrees of freedom, which is like a spin 1/2. The first thing we want to see to be sure is, do we have the Bosonic integer quantum Hall effect for nu equal to? For that, we can just run some iDMRG calculation and check at the entanglement spectrum. So this is the entanglement spectrum that you get out of the simulation. That's the entanglement levels as a function of the momentum. You have two different symbols because you can address different spin sectors. But overall, what you observe here, the Bosonic integer quantum Hall effect, you know the edge properties. You know that you have two counter-propagating edge modes, one charge mode and one neutral mode, so that the whole conductance is the 2e squared over h. But if you look at thermal conductance where both will contribute, you get 0. And if you look at the entanglement spectrum, basically you have here one of the propagating edge mode, another one here, and then you have to get the full spectrum, you have to combine these two modes. So that's why you get this V-shaped structure with all the levels here. And really, you can just count how many states you have per momentum sector and check that it matches the picture of this two propagating edge mode. OK, so we are good. The model has really this new Bosonic integer quantum Hall effect at nu equal 2. So let's move on and try to see what's going on at 4/3. Remember, the next step is to see if the Halperin state, for which this model is an exact ground state at nu equal 2/3, if it has a particle Hall partner at 4/3. And actually, there was still some debate about the nature of the phase at 4/3. He had two competing proposals. The first one is a non-abelian spin singlet state, proposed a few years ago by Haldane and Schoutens. It's a generalization of the mode state to the case where you have some spin degree of freedom. It has non-abelian excitations, which are Fibonaccianians. It's exactly what you need for topological quantum computation. And the edge structure is known because basically the state is built out of a conformal field theory, and you know exactly how to describe the edge properties. The particle Hall conjugate of the Halperin state 221 that you can also rewrite as some Gen composite wave function. On the other hand, has only abelian excitations, but we also know how to deduce the edge structure just by using this particle Hall conjugation. The particle conjugation also tells you, when you know the edge structure of one state, what will be the edge structure of the particle Hall conjugate. So these are the two main suspects for the 4/3 state. People already tried to discriminate between these two proposals, mostly using exact diagonalization. But unfortunately, none of them is conclusive in favor of one or the other. So can we revisit this problem using iDMRG? The answer is yes. And once again, we use the same probe to distinguish between the two proposals, namely the entanglement spectrum. So there are, once again, you can infer the edge structure from the particle Hall conjugation and the edge structure of the Halperin 2-to-1 state. But you can also directly brute force look at the wave function, a model wave function that is also described as fourth state, particle Hall conjugate state, and compute its entanglement spectrum, at least for small system size. And what you can see here is the result from the model wave function on the sphere geometry and the iDMRG result on the cylinder, where there is no bias. You don't assume anything about what is the actual ground state of the system, match pretty nicely. And well, you can also do like count how many levels you have, and this is an agreement with the edge structure of the particle Hall conjugates of the Halperin 2-to-1 state. So and we have no sign of the NASS state in this numerical simulation. Of course, you would like also to be sure that this is really a gap phase. And this is where sometimes going back to exaggeration can be helpful. It's sometimes easier to extract the gap there. Of course, we don't have many points. Remember, that's an exponentially complex problem with the number of particles. So we can, even if you use like big computers, there is no way you can do 100 particles for the system. So we have only a few points, but clearly compared to some other cases, we don't see any this gap going to 0. So that's the red dot for third state. And as a reference, that's the gap for 2/3 state that you can evaluate more accurately, also using hexagonalization. So the final step is to see what's going on at nu equal 1. Remember, for fermions at 1/2, we have this gapless composite Fermi liquid, so which is tightly related to this particle Hall symmetry. So for two component bosons at nu equal 1, what was shown from a theoretical point of view is if you have both the SU2 symmetry and the particle Hall symmetry, if both symmetries are preserved, then the system cannot be gapped. So therefore, if we have a composite Fermi liquid at nu equal 1, this is you should get that if you have the particle Hall symmetry, because our system has a SU2 symmetry. There was previously some hints of a composite Fermi liquid using hexagonalization of the sphere. So what we did here to be sure that this is indeed a CFL was to use both a mix of hexagonalization and iDMRG calculation. But here we use a torus geometry. So what we do is the following. We take our bosons, we put them on a torus, and we just diagonalize the Hamiltonian. We do that for 14 bosons. The reason why is the following. We use a twisted torus. So if you look at the lattice in momentum space, it looks like a triangular lattice. And you have your composite fermions, which are basically made of one boson tied to a flux quantum. And of course, they have a spin too, so a blue or red spin. And you try to form a Fermi C out of these composite bosons. And that's exactly what you do in momentum space here. This is the lowest energy configuration that you can create. And you can compare to what you get from hexagonalization. So this is the result, the low energy landscape that you obtain by ED. And as you can see here, there's a red dot in the center that corresponds to configuration with 0 momentum. That's exactly what you get from this picture here. You can, of course, try to see what is the lowest excitation that you can create out of this Fermi C by moving, let's say, one particle and see if it matches the landscape, the energy landscape that you have here. Maybe a more striking way is to what's going on if you remove or add one boson to your system. And that's what we do here. We remove one boson from the system. So basically, starting from this composite Fermi liquid here, see we just remove one, like the red arrow here. We can do that, of course, at different places. And we can compute the momentum, and we get 6 states at times 2 for the degeneracy. But these are the 6 states lowest energy state that we observe in ED. You can do the same by adding 1 particles, and you have also 6 options, and these are the 6 options here. So this CFL picture really captures what we observe in numerical results. So since I'm running out of time, just in a nutshell, you can do more advanced calculation using iDMRG to analyze the CFL. But at the end of the day, you can map out the shape of the Fermi surface, and it's really good agreement with what we obtained from ED or the notion of a Fermi sea. So let's conclude here. Maybe I should start with this one. That's maybe the message, the technical message of this talk. So we have a system which has bosons in a system with band and insulator. And you could have an emerging particle Hall symmetry with a twist, is that you need this additional internal degree of freedom. But more generally speaking, I think that if you look at fractional quantum Hall effects, it's not a young topic. It's more than 30-year old. And still, we find new results, all the time, which is, I think it's kind of fantastic. And the reason why sometimes we can probe this system much more is because we have made lots of progress in both in techniques from a numerical point of view, like this iDMRG calculation, but also by understanding the profound nature of the state that we are dealing with, like what is the entanglement properties of these topological phases. OK, that's it. Thank you.
Time for a few questions.
Yep.
Maybe a very short technical question. You said the time of iDMRG grows linearly with the diameter?
No, the exponential of the diameter. The entropy, it's Narialo, so it's the entropy grows linearly with the perimeter of the system. So it's still an exponential problem, but it's an exponential gain.
Further questions?
Bosons can fill any numbers of particle at a site. So the local Hilbert space is very large. So the metric product state has a dimension of d to the power L.
So the reason why you're able to perform, you're right, that's exactly what was mentioned. It's still an exponential problem with the system size, right? The complexity of the algorithm is still exponential for this specific setup. I think you were there during the lecture. So for 1D system, it's a different story for a gap phase. But here, even if it's a gap phase, you still have to, in principle, to take infinite matrices. But now, what basically the iDMRG will do is, if you take the entanglement spectrum, is to make a truncation at some point, to decide to throw away some of the entanglement levels which are too high, which correspond to low weights in the reduced density matrix. So you still have, especially because you have this linear dispersion relation here, you know that when you have a topological phase, you will still capture accurately the wave function, because all you need is basically the low entanglement part of the entanglement spectrum. So you can still use a finite size MPS to represent this state with a very good accuracy. Of course, in principle, you need an infinite matrix.